Hi everyone, Anna here, your tech fairy, bringing a bit of Halloween magic. Ever wonder how Linux keeps track of all the files you have opened? With the file descriptor table, a behind-the-scenes hero that makes it all possible. So brace yourself for another diagram featuring our rockstar. And who's better to teach it than Sailor Moon herself? Moon, prism, power, make the tech magic happen. Woo! Alright, let's start with the basic. Before you can start reading or writing from a file, you need to open it. Alright, then to open a file, you can just type int_fd equals, and then we use an open system call to open the file. And the first parameter is the string path to the file, and let's just put the blue txt because we're already in our working directory. Next, we add the flags for permissions, and let's set it to read and write. And this is assuming that the file already exists. Okay, I've got two empty files here all set up and ready for us to work our magic. Check out this integer returned by the open system call. That's where our file descriptor comes into play. Each process has its own little list of open files, and that list is made up of these magic numbers called file descriptors. You can call it FD if you could like that. For example, you can have FD3 associated with file called blue. These numbers are actually indexes that point to another structure called the file table, where all the juicy details of each file live. The file table is a kernel-wide and shared amongst all the processes. It contains information about each open file, including a pointer to a file's inode and other metadata such as the file position and access mode. For example, the metadata for a blue file could be stored in entry 100 of the file table. On the other hand, the file descriptor FD table is per process. So if we have another process running, it would have its own FD table. Check this out. Imagine we create another process, process B, by forking our original process A. In this scenario, process A is a parent and the process B is a child. Process B will have its own FD table, but they will already include an entry for the open file. That's right, process B inherits the file descriptor FD3 from process A because it's the child process and the file was opened before the fork system call. This means they share the same file offset and permissions. So, if process A reads from or writes to blue file, it will affect where process B will read or write next. Any changes to the file position by one process will also reflect in the other. Now imagine we have another process that wasn't created using a system called fork. Let's call it process X. We can head to a different program and open the same blue file using open system call and set the flags for read only. Process X can open this file with different permissions if it wants to. In this case, each process has a unique file descriptor pointing to a different entry in the file table. Right, process A and X have independent file offsets and access modes. For example, if process A reads 100 bytes, it won't affect process X read position in the file. Both processes manage their own state for the file independently. You can think of the file descriptors as little index cards that point to the file you've opened. They are always unique and non-zero integers. So instead of having to write the full file path every time you read or write to the file, you just reference that index card. Your file descriptor and Linux knows exactly where to find your file. Simple, right? Let's also talk about some special file descriptors that are always present in the table. 0, 1, and 2. These are default file descriptors, and 0 is reserved for standard input, like the keyboard. 1 is for standard output, which is your terminal window, and 2 is for standard arrow, which can also be sent to your terminal. So both of our processes would have this default file descriptors. Whenever you open a file, it's added right after these default entries, meaning your new file descriptors start at 3 and go up from there. Each process can have thousands of these little descriptors, By default, it's up to 1024, but you can raise that number up to over a million if needed. But remember, it's never a negative integer. So your return value of -1 is your system way of saying, oops, something went wrong. Definitely keep an eye out for that when opening files. Now let's see the file descriptor table in action. When a process opens a file, Linux makes an entry in the file descriptor table. Let's imagine our process A wants to open another file. We already know how to open a file, but this time we need to set our first parameter path to another file. We can call it ping.txt. Next, we add flags for permissions. And this time, let's use a read-only permission. Now let's reflect this in our FD table, okay? The system will automatically assign the smallest available file descriptor, which in our case is 4. So our open system call will return 4. This entry also includes information on where the file is stored on a disk, which is its path, which is ping.txt. We've also indicated the access mode for our file. And the file access mode is read-only. We'll go into the file table along with other details like current position in the file, the reference count, and the pointer to its inode. This inode pointer then connects to yet another table, the Inode Table. So Inode Table is a data structure in the file system that stores metadata about each file, like its size, permissions, timestamps, and pointers to its actual data blocks on the disk. But someone better stop me before I dive into Inode Table and turn this video into a short and sweet to a long and boring lecture. And long and boring, that's what professors' lectures are for. Here we learn, have fun, and do it fast. Yay! If you're still watching, don't forget to sign up and give me a like. Anyway, so the file assigned 4 as a file descriptor for our ping file. Now, whenever you want to access the file, you just pass the fd to kernel, and it knows exactly where the file is and how you want to access it. Now, what happens when you want to read from this file? Well, then you call the read system call. Linux will look up the fd in the file table, find the corresponding file entry, and pull the data for you. Let's take a peek at the basic read operation. To use the read system call, we first need to define our buffer. Then we use a read to pull the data from the file descriptor, fd, into our buffer. And we also specify the size. So here in our read example, fd will be 4 because we're reading from the ping file. And we can also read from the standard input or our keyboard. And in this case, our file descriptor would be 0. Because 0 is reserved for standard input in a file descriptor table, and the rest will stay the same. Okay. Now, writing to a file is pretty similar to reading. Let's say you want to write something to that file. You'd use the write system call. For the write system call, we need the file descriptor of where the data is going to be written. Then we put a pointer to a string containing our message. Oh, oops, we forgot to add the message, but that's not a big deal. Instead, we just stick our message right in here and indicate its length. And I think it's up to 10. Okay, should be 10. Okay. Linux checks the file descriptor table to locate the file associated with that fd. It would go and find our ping file, but then it checks permissions and it won't write to it, hey, because it's a read only. Do you see here in our process table, we said read only permissions? It corresponds to what we put in our open system call. Let's run it and check. You see, nothing's there. Otherwise, it would have written to it without any issues. So, if we use the file descriptor for our blue file, which has read and write access, we'd be able to append our message to it, no problem. And we could also use 1 to write directly to our terminal, not to a file, because file descriptor 1 is associated with standard output. Also, don't forget to close your file descriptors like I occasionally forget to. We don't want them hunting us like a ghost. Okay, so let's run our program really quick and check if we see our hello pink message in the blue file and in our terminal window. Here it is. Let's check the blue file now, and our message is here. Perfect. As you can see, the pink file still doesn't have our message. All right, and that's a wrap up on the file descriptor table. The unsung hero keeping all your open files in check, so each process knows exactly where to read and write. If you enjoyed this Halloween adventure with your tech fairy who is rocking the Sailor Moon look today, don't forget to like and subscribe. And if you've ever been haunted by a lingering file descriptor because you forgot to close it like I do sometimes, share your story in the comment section below. No judgment here. If you want Sailor Moon to do another videos, please let me know in the comment section also. And I'm your tech fairy signing off. Moon Prism Power, make the tech magic happen. Woo!